Welcome once again students to the class of topology, and we'll go ahead on the topic of separation axiom in this video. So where we have stopped in the last video, I promised you that in the next video we'll talk about completely regular spaces and its properties. So that's what we are going to do today. So first of all, definition of a completely regular space. So first the definition, and then we'll go ahead on theorems of completely regular spaces. So what a completely regular space is? Let X top be a topological space. X top is said to be completely regular. In short, we say CR space, completely regular space, if for every closed subset f of x and for x not belonging to f, we have a continuous map. F from x to the closed interval 0, 1, that is the subspace of the usual topology, x to 0, 1, such that image of the point x, that point x is 0, and image of every point of f, this f, the closed subset f, is 1. If this condition is satisfied, we say that the space is completely regular, that means a CR space. This is the definition. So diagrammatically, let us see what a completely regular space is. Let us see the space diagrammatically. So here we are having the space X with the topology tau defined on it, and if you take any closed set here F and a point X not belonging to X, then there will be a map F from X to the closed interval 0, 1, such that image of this X is 0 and image of every point inside the set F, is 1. So this is the diagrammatical presentation of CR space, completely regular space. And now we'll move on to some theorems, some results of completely regular spaces. I'll start from some easy results, and slowly we'll move on to a little bit typical results. So the first of all, a very easy result. But before going on to the theorem, before going on to the results, one more thing I want to tell you, that if a space is CR, that means completely regular, as well as T1, then it will be called T3 and half space. If a topological space is completely regular as well as T1, then it will be T3 and half space, also known as Tikhonov space. So what is a Tikhonov space? It is a completely regular space as well as a T1 space. So now we'll move on to some important theorems. The first one I'm going to take is, first I'm going to write the statement of the theorem, and then we will prove it in a very easy way. So theorem is, a topological space X top is completely regular if and only if for every point x belonging to x and for every open set G containing x there exists a continuous function f from the space x to the closed interval 0 1 considered as a relativized subspace of usual topology such that f of x is 0 and image of every point of x minus g, that means the complement of g, is 1. This we have to prove. This is the first one, and it is, as it is seeming, it is really very easy. It will just be proved directly from the definition of completely regular spaces. I'm going to rub the statement and then I'll move on to the proof. So better if you write the statement in your notebook by stopping the video and then move ahead to the proof. So proof of this theorem. Since it is if and only if, so we'll have to prove the direct part of the theorem as well as its converse. So first, let x top be completely regular. We have taken x top to be completely regular, and let x be a point of x, let G be a tau open set, let G be a tau open set such that x belongs to G. Since x belongs to G, this means x does not belong to G complement. Now, G was open. What about G complement? Definitely it will be closed. So a closed subset of x and a point x not belonging to that closed set. Therefore, by definition of complete regularity, by definition of CR space, completely regular space, there should be a continuous function. There should be a continuous function f from closed x to closed interval 0 1 as a subspace of usual topology such that image of x is 0 and image of every point of G complement is 1. And what is G complement? G complement is nothing but x minus G. So this is the direct proof. You have taken G, then G complement, and using the definition of complete regularity, the proof is complete. Converse is also very easy. So we'll move on to the converse part now. Let the given condition holds. That means for every open set G containing x, there exists a continuous map f such that f of x is 0 and f of every point of the open set is 1. So we have to prove that the space is completely regular. Since we have to prove that the space is completely regular, from where we have to start? We have to start by taking let f be a closed set and let x not belonging to f. This is from where to start. And what we have to do now, we have to arrive at a point where there will be a function f continuous from x to closed interval 0 1 as a subspace of usual topology such that image of the point x is 0 and image of every point of f is 1. That is where we are to arrive. X does not belong to G means x belongs to f complement. F is closed, so F complement is open. So what you are having, a point X of the space X and an open set containing that. So therefore by the given condition there exists a continuous map, continuous function F from X to 0, 1 such that image of X is 0 and image of every point of F complement, image of every point of F complements complement, because in the statement it is G and here you are having G complement. So G complement means F complements complement is 1. But what is complement of a set? The set itself. So this means F of X is 0 and F of F is the singleton set 1, and that implies that the space is completely regular. So this was a very easy theorem which was proved directly using the definition of the complete regularity of a topological space. And now we'll move on to the next theorem, which is again very easy. Theorem is prove that every completely regular space, CR space, is a regular space. Hence, show that every T3 and half space is a T3 space. So this is the theorem. First we'll prove that every CR space is a regular space. So proof, I'm going to start by taking X top to be a CR space. So let X top be a completely regular space and we have to show that it is a regular space. If we have to show that it is a regular space, we will take a closed set and a point X not belonging to that closed set, and then we will find two open sets, one containing X and one covering the whole of the closed set, such that the intersection of the open sets will be phi, and that will show that the space is regular. Now X top is regular. We have to show that the space is regular, so let F be a closed subset of R of X, because the topological space we have taken X, and let X be a point not belonging to F, because we are going towards the regularity of the topological space. Now F is a closed subset and X is not belonging to F. Given the space is given to be CR, completely regular. So therefore, by CR, complete regular property, by CR property, we have that there exists a continuous function F from X to 0, 1 such that F of X is 0 and F of every point of F is the singleton set 1. Here we have used the property that the topological space X top is given to be completely regular. Now I am rubbing the board as I need the space to write more. Now consider this 0, 1. 0, 1 is a subspace of the usual topological space of real numbers R. Since R is a Hausdorff space and Hausdorffness is a hereditary property, so 0, 1 considered as a subspace of R with usual topology is a Hausdorff space. So now 0, 1 is a T2 space. 0, 1 is a T2 space. 0 and 1 are two distinct points belonging to this closed interval 0, 1. Therefore, using the definition of T2 space, there must exist open sets G and H such that 0 belongs to G, 1 belongs to H, and G intersection H is phi. Here I have used the definition of Hausdorffness, T2 spaces. So 0, now G and H are open sets. So where these are open sets? Here in the subspace of RU, usual topology. The function f is continuous, and we know that inverse continuous image of an open set is open. So G and H are open. That means f inverse G and f inverse H are open in X. So now f inverse G and f inverse H are open sets in X such that, here I will use the continuity of the function f. So f inverse G and f inverse H are open such that, now 0 belongs to G, and you know that your fx is 0. Your fx is 0. 0 belongs to G. That means your fx belongs to G. Fx belongs to G means your x belongs to f inverse G. I am writing back here, taking back step. X belongs to f inverse G. This is one thing. Secondly, your f of f is equal to 1. F of f is equal to 1. And since 1 belongs to H, this singleton set 1 is a subset of H. And f of f is a subset of H means your f is a subset of f inverse H. So I am going to write it here again, that f is a subset of f inverse H. And one more thing, your G and H are disjoint. Their intersection is phi. So this means f inverse G and f inverse H, their intersection is also phi. So what you have done, you have taken 2 points 0 and 1. Sorry, you have taken in the starting a closed set F not containing a particular point X, and now you have two open sets f inverse G and f inverse H, f inverse G containing X and f inverse H covering F, and intersection of these two open sets is phi. That means they are disjoint, and that is the definition of regular spaces. So this means your space X tau is regular, and this proves that X tau is a regular space. So we have proved that every completely regular space is also a regular space. So you have proved that CR implies R. Completely regular implies regular. Now, completely regular plus T1 will imply regular plus T1. CR implies R, means CR plus T1 implies R plus T1. And what is CR plus T1? It is T3 and half. And R plus T1, it is T3. So that means every T3 and half space is also a T3 space. So it is one among the theorem. And one more theorem I am going to take today in this video about complete regular spaces. And this theorem is, write down the statement first. Theorem: show that property of being a complete regular space is hereditary property. That means subspace of a completely regular space is also a completely regular space. This is what we are going to prove now. So I'll start with the proof now. Let X tau be a completely regular space and let Y tau Y be a subspace of this topological space X tau, and we have to show that Y tau Y is also a completely regular space. For that, from where we have to start? We will take one closed set here and a point not belonging to that particular set, and then we will try to find a continuous function from Y to the closed interval 0, 1 as a relative subspace of usual topology such that image of that particular point is 0 and image of every point of that particular closed set is 1. So let B star be a closed, you can say tau Y closed, be a tau Y closed set, and let X be a point not belonging to B star. One thing you must note that B star is a tau Y closed set. How tau Y closed sets are constructed? Some tau closed set intersected with Y. So B star will also be a set of the type some tau closed set B intersected with Y. So definitely B star, there exists, you can say there exists tau closed set B such that B star is B intersection with Y. This is from the construction of closed and open sets in the subspace. So X does not belong to B star we have taken. Now X does not belong to B star. So this means X does not belong to B intersection Y. But X is in Y because we are considering here tau Y closed set and we are taking the point X such that X is in Y. We are taking a point X of Y which does not belong to B star. So X does not belong to B intersection Y, but X belongs to Y. X belongs to Y, does not belong to their intersection, means X does not belong to B. And X belongs to Y means X belongs to X. So X is a point of X which does not belong to B. And what is B? B is a closed set, tau closed set. X tau is CR. X tau is CR. We have taken X from X and a closed set B, tau closed set B, such that X does not belong to B. From complete regularity of X tau, we can find a continuous map F from X tau to 0, 1 satisfying the given condition. So therefore, there exists a continuous function F from X to closed interval 0, 1 such that whenever I am writing closed interval 0, 1, you must you must understand that this is considered as a subspace of the set of real numbers with usual topology as a relative subspace. So there exists a continuous function such that image of X is 0 and image of every point of B is 1. Here we have used the complete regularity of the space X tau. But where we are to reach? We are to reach at the continuous function G from Y to 0, 1 such that G of X is 0 and G of B star is 1. That is the point where we are to reach. Now consider the restriction map G, restriction map of F to Y. That means we have restricted the domain of F domain of f was x, and now we have restricted it to the y. So G is a restricted map of f from y to closed interval 0, 1. Consider G is equal to f restricted to y from y to 0, 1, such that since it is a restricted map, what will happen? G of x will be equal to f of x for every x belonging to y. It is the definition of restriction map. So I have taken the restriction map, and now one thing is clear, that restriction map of a continuous map is continuous. So this means G is continuous. Then G is continuous because f is continuous. Now G of x and G of b star, we have to take x. G of x is f of x, but f of x is 0, so G of x is also 0. One thing is clear, that G of x is 0 because x is a point of y, and for every point of y, G of x is same as f of x because G is a restricted map of f restricted to y. Now G of b star. Now let you can say, let x be a point of, y be a point of b star. Let y be a point of b star. So this means y is a point of b intersection y. Y is a point of b intersection y. That means y belongs to b and y belongs to y. And for every point y belonging to y, G of y will be same as f of y because this is the restriction map. So G of y is equal to f of y, but y is in b and f of b is 1, so f of y will also be 1, so it is 1. From where you have taken y? You have taken y from b star, so G of y is 1 for every y belonging to b star, or you can say G of b star is 1. So we have taken a tau y closed set b star and a point x not belonging to b star, and we have obtained a continuous function g from y to closed interval 0, 1 such that g of x is 1, g of x is 0, and g of b star is 1. That means image of every point of b star is 1, and this is the definition of completely regularity. So this means your y tau y is completely regular space. So complete regularity is a hereditary property. So I'm going to stop this video here. In the next video we will have more theorems, more propositions, more lemmas, more examples, more questions from completely regular spaces. Till then, thank you once again.